Hello. This is a series series of videos where we will be having a reading group where we are studying quantum processes by Bob Koik and Alex Kissinger. So today we will start with the third chapter because the first two chapters are just sort of like intros. So these all topics are not very important. So we'll dive straight into the third chapter. Before that, Nishchit will introduce ourselves.
Yeah.
Cool. So you start and then I'll start.
Yeah. So hello everyone. Myself Nishchit. I'm in my fourth year right now in electronics and communication. I kind of like wetting my hands in quantum computation and quantum mechanics basically for some time. Yeah, this is a good opportunity for me.
All right. My name is Farhan. I do math as a hobby, so I just find myself all over the place most of the time. And yeah, so this is one of a couple reading groups that we will be conducting. So stay tuned. All right. So chapter 1, it'll work like this, Nishit. You go one para, I'll go one para. If we have any, or you go one para, I go one para. We pause if we have any comments, and then we continue after finishing said comment. And we will probably go really slowly. So this will take a bunch of videos to cover the entire book. But the point is to pay attention to like our comments about each thing. Okay, so I'll start. Chapter 3, processes as diagrams. In this first real chapter, we provide a practical introduction to basic diagrammatic reasoning, namely how to perform computations and solve problems using diagrams. We also demonstrate why diagrams are far better in many ways compared to traditional mathematical notation. The development and study of diagrammatic languages is a very active area of research, and intuitively obvious aspects of diagrammatic reasoning have actually taken many years to get right. Luckily, the hard work needed to formalize the diagrams in this book has already been done. So all that remains is to reap the nice benefits of a nice graphical language. All right, you can go ahead.
Yeah, sure. So, should I open it on my own laptop or?
Yeah, I can send it to you if you want, or you can read it through the presentation.
Yeah, I guess it would be better if you could send it to me.
Awesome. Okay, I'll just pause the recording and I'll send it.
So, yeah. Along the way, we will encounter Dirac notation. Readers who have previously studied quantum mechanics or quantum information, the information theory may have already seen Dirac notations used in context of DMX. Here, we'll explain how it arises as a one-dimensional fragment of the two-dimensional graphical language. Thus, readers not familiar with Dirac notation will learn it as a special case of the graphical notation used throughout the book. We also introduce the notation of a process theory, which provides a means of interpreting diagrams by fixing a particular collection of physical, computational, mathematical, or ethical systems, and the processes that these systems might undergo, like being heated up, sorted, multiplied by 2 or cooked.
Right. So I just like to make a comment. So over here in the book, it's mentioned process theory, and I recently came across a paper, Intro to PA, Intro to Process Algebras. So I came across this in sort of a different context. It was like they were going from logic to formal language to then programming languages and stuff. And this is where it sort of came up. And I think maybe later in one of the smaller videos, we can like go through this because it's only 35 pages. So I think maybe after chapter 1, we will do this, after this third chapter, we will go to Intro to PA and then we'll continue from the next one.
Following up on that, what do you know about like Dirac notation?
Dirac notation, I know it. Yeah, it's just bracket. Yeah.
Mhm.
Yeah.
Like, what part of mathematics does it come in?
So, inner products. So you have your vector space, and your Dirac notation is just a nice notation for going about explaining inner products. So you can have many different kinds of inner products as well. And so Dirac notation is just a trivial one because it's only just the regular Euclidean inner product. You can have fancier inner products too for different kinds of algebras. So, and another interesting thing is, before we go for Dirac notation, we have to define Hilbert spaces. So just the fact that Hilbert spaces are like, do you say, what's the requirement for Hilbert spaces? Just an inner product, or what was it?
As far as I remember, Hilbert space has two parameters, right?
Right.
Sorry, two. One is of course the inner product spaces. The one, I guess inner product is it's not exhausting, like it's not exhaustible condition. There is I guess for example, now Euclidean space, it's a Hilbert space, right?
Yeah. Yes.
Even the function spaces are Hilbert space. Probably.
Yeah, that's why. Yeah, that's why they're used in Hilbert spaces. And I remember hearing a lot that they're infinite dimensional, but I don't remember Hilbert spaces necessarily being infinite dimensional. They're infinite dimensional in the context of function spaces, but not so in general. And I'm wondering if it is in the case of quantum mech. I don't think it is, right?
As far as I've read, I guess like inner product, like being real or complex inner product space.
Right. I think it's a complex inner product space, right, for this context.
It can be both because, of course, we use the complex part more, but as the Hilbert space goes, it can also be, like the real inner product space.
I see.
Probably we'll go over that sometime later.
Right. Hilbert spaces are like a subset of Banach spaces, right?
Yeah.
Cool. That's about as much as I know with respect to Hilbert spaces.
Yeah, that's it. Even like if we go in a little bit more depth, it gets a lot more interesting and a little difficult to grasp.
Banach spaces are what norm is defined, right? Doesn't matter about inner product anymore.
Yeah.
Right.
This is a special case of Banach space.
Right. Cool. So, as we pointed out in the introduction, taking process theories as our starting point represents a substantial departure from standard practice in many disciplines. Rather than forcing ourselves to totally understand single systems before even thinking about how those systems compose and interact, we will seek to understand systems primarily in terms of their interactions with each other. This is a very, category theory point of view. This is, for our viewers, this is called the Yoneda lemma. And this is just a perspective where an object is really defined only by its relation to all other objects. So it means to say that any definition of an object is purely an extrinsic characteristic, no matter how intrinsic it may be as a property, can only be defined by the relation of that property with other properties of equivalent properties in other objects. I watched a video on it yesterday, that's why I'm happy to see it.
Yeah.
So, rather than trying to understand Dave the Dodo by dissecting him, at which point he'll look pretty much like any other fat bird, we will turn him loose in the world and see what he does. This turns out to be a very close in spirit of category theory.
This part, it's like the soul of whatever you call like category theory, because it's not plainly something that you could do only on your, like something of a subset. It doesn't work like that.
Yeah.
It's something you do and understand, not just understand and then do it.
Yeah, exactly.
one thing about category theory.
That's true. That's very true. Yeah. This is your turn now. 3.1.
Yeah, sure. Okay. So as we continue, let's have a look at how diagrammatic language uses a general way to speak about processes and how they compose and show that these diagrams provide a rigorous mathematical notation on par with traditional mathematical formulas. So one comment I would like to make is like when we start learning math at first,
Right.
we take mathematical notations as something as like just something to convey our point.
Right. Right.
But like when we move to advanced math or higher mathematics, like notations are the way we have to program ourselves to think, because not everything is exhaustively like based on formulas.
True.
Sometimes notations, they abstract away a lot of parts, but that's for our benefit so that we can, bring up something that's underlying, and you can't do it by maybe something like brute force.
Yeah. So, like, for example, if you were looking, exactly what category theory does, it just loses information by compressing the set into just these objects. And so that's literally the philosophy of category theory. Yeah, that's a very nice comment. Yeah, that's very true. You can read on.
Yeah, sure. Okay. Now, process as boxes and system as wires. I have some interesting comments on this. So we shall use the term process to refer to anything that has 0 or more inputs and 0 or more outputs. For instance, the function f of x comma y equals x squared plus y is a process which takes two real numbers as input and produces one real number as output. We represent such process as a box with some wires coming in the bottom to represent input systems and some wires coming out the top to represent output systems. For example, we could write the function x squared plus y as this. So again, sorry to stop here, but one very interesting comment.
I love your comments, yeah.
So we have, I'm from electronics, right?
Yeah.
We have something known as control systems, and another parallel of it is something known as network theory.
Tell me.
As I told, and with respect to category theory, right? We sometimes take it as a black box. We abstract out a lot of things and then get to the finality, right? So these concepts in electronics, they work the other way. We see what the black box is giving and kind of try to reverse engineer what the box might be.
I see.
Usually when you abstract things and get to an output, usually you don't think about what's happening in the box as a process. But as this part of the book that tells that they use boxes for a function, like it's a normal thing that they usually use for all the functions. But here, like, it's very analogous to whatever I have seen in electronics. So yeah, just a point to say that something transcend topics.
So, when I had a question, so you say given an output and an input, you're going to reconstruct your black box, right? Can there be is it always a unique black box? Can you have more than one black box giving you the same thing?
So, it depends. When we reverse engineer, right? When we figure out what the input and output are, we get some parameters.
Right.
So you can take parameters and design them in multitude of ways. That there is some set of ways which you could do.
So what are these parameters?
For example, if you take a box, okay,
right,
you have something called as an input impedance and an output impedance. Impedance is nothing but a glorified resistance, I would say.
So is there something like it has to be preserved or conserved?
Yeah, actually in physical systems, the conservation doesn't work out because when we use some elements like resistors, they lose some of the energy. So energy is a concept, to be honest. But when we look at the macro level, it's usually comes out. What goes out, what goes in should come out.
Right.
Sometimes there are some systems which are designed to give half goes in or double of what goes in.
Right.
Like we have transformers, and like there are multiple parameters that you take. And then you have like first number of ways in which you can design the box or whatever is inside the box. That's
Okay.
where you are basically we have topics for network analysis. So such parts come up.
Tell me more. Wait, so I think we will finish up to like we'll finish a decent chunk and then we'll talk about this more at the end because like I want to get into the
sure.
details. No, do you want to say anything more though?
Yeah, that's done. I'm done with it.
Okay. One small comment I want to make. This looks a lot like logic gates and quantum gates. So like that's literally the way I start thinking about it. And I think that's literally the kind of like comparison they're trying to do. So they're immediately just gonna say every gate is some sort of process.
Yeah, I mean, gate itself is a process.
Gate is a process, yeah. I think, yeah. So labels on wires are called system types or simply types. Just a small comment I want to make that there is a field called type theory that is very important in computer science, especially for a smaller field, not a smaller field, a subfield called functional programming. So this is all pertaining to homotopy and homotopy type theory, etc. So all the good stuff.
Yeah. I mean, for viewers, if you need an example of a functional programming language, one of my favorite, which is closer to my heart, is probably Haskell.
Haskell, yeah.
I like the symbol also. It's like
Yeah, it's a lambda, yeah. Yeah. So similarly, a computer program is a process which takes some data from the memory as input and produces new data as an output. For example, a program that sort lists looks like this. You have a process quick sort and you input lists and you output lists. The following are also perfectly good processes. You have binoculars that take light and give out light. You have breakfast. You have cooking that takes your breakfast, takes your eggs and bacons and gives you breakfast. You have your baby that gives you food and that you give food and love and gives you noise and shit. So another thing is this bottom to up approach of reading reading outputs. So clearly the world around us is packed with processes. Note how sometimes a box is labeled with a process that occurs over time, the process of cooking breakfast. While other times we label the box with an apparatus. Typically, this means the process of using this apparatus to convert input systems into output systems. So, in some cases, wires in the diagram may even correspond to actual physical wires. Okay.
Yeah. Shall I continue?
Yes. Yeah.
Just a thing. Wouldn't it be better to add some arrows?
Yeah. I suppose so.
The bottom top approach.
This is like somewhat old. Like it's older than now. There's another book that he wrote, and in that maybe they might have done that, or we can just get used to putting in the arrows ourselves.
Or just
Even I think it's a bit too ambiguous. Just having a wire between them is not clear which is the output and which is in.
because, for example, with the baby part, right?
Right, yeah.
The thing
You can't tell if the baby is eating noise and food.
or more than that, the baby takes love, like a baby needs love. Also, baby gives the love. Like it's
True.
kind of bi-directional.
So, right. So you can, I think that's taken care of, just having love on another side is an extra thing. I think they've taken a very stubborn baby here, but they will just have another wire coming out with love.
Very good.
Cool, okay. So,
Shall I continue?
yes, your part.
Though, of course, this needs not always be the case. Wires can also represent, for example, aligning approaches on lab equipment or shipping something by boat. The important thing is that the wires represent the flow of data or more general stuff from one process to another. As we have seen, we can wire together simple processes to make more complicated processes, which are described by diagrams.
Right.
Yeah. So, yeah.
You can read further.
In such a diagram, Outputs can be wired to inputs only if the types match. For example, the following two processes. Yeah. G is a process and H is a process. G takes in B and D and gives out A and C, while H takes in A and D. Just make sure that these two are actually the same, and these two are actually the same. So here you can see that it can be arranged in two ways, and I have no idea what the skull is doing here.
I think the skull means you can't do it.
Yeah, maybe.
It's like,
So yeah, this probably shows the restriction in wiring so that there is a match of inputs and outputs. So pretty interesting. Again, analogous to what we have. We have a field called radio frequency.
right.
You know how the satellites and all work, right?
Yes.
Yeah, that similar thing comes into something called as transmission lines. So it's basically your two power carrying lines which go throughout the country distributed for the power distribution basically.
Mm-hmm.
So in fact, we have something known as impedance matching. So
Right.
as I told, impedance is glorified resistance.
Yeah,
So when impedance matches with each other, so there is less loss.
I see. So for this case, it's actually something that minimizes your loss.
Yeah, I mean, usually when you're designing a system for RF, impedance matching is always very important. And again, like similar to this, if A, C, B, D are the impedances, and D and A are the impedances, A and A will go together very well,
Yeah.
and C and D will go together very well. But again, if you do this, you get huge amount of loss, which is not good.
That's actually very interesting because it's sort of like this is a subset of what you typically do. Like if in a very loose structure, you can match all these different kinds of things together. But then if you try to assign some sort of energy to the system, which would be a very interesting analog to explore. If we try to take this sort of connection thing and we try to assign an energy and we try to take the minimization of that energy, then we should basically get this process diagrams. That's a very nice way to look at it because then whatever we have before the minimization is going to be very interesting structures.
Exactly. So yeah, I believe that's one reason, right? People call mathematics as the language of universe because
I agree.
You find similar things everywhere.
Exactly. You match one thing, you finally have you suddenly have a tool set for everything else.
And a new branch out of it, you never know.
Yeah, actually. Go on.
Okay, this is funny. Yeah, this restriction on which wiring I load is essentially part of the language of diagrams. In that it tells us when it makes sense to apply a process to a certain system and prevents occurrences like this. So, as we were discussing about AB previously, the poo can
You can't
be
solve
sorted,
it.
but the output is not something you want, it's still poo.
Well, surprise, your output's going to be pretty much the same.
Yeah. Unless the baby has been fed something bad. And, the food-
Unless the baby poops in binary.
This is fun.
Elon Musk looking at you.
So basically, that might be the future of hex dump.
Right.
So I guess we can continue.
Oh, okay, yeah. So yeah, you can prevent occurrences like this, which probably wouldn't be very good for your computer, much like data types in computer science. The types on wires, a small note I want to make, that just an observation. I've noticed that data types being data types, we often study them as some sort of consequence of programming, right? That you have to obey them. I think they're very intentional structures that were as they go from logic to formal language to and so on. I think data types is.
One thing I can tell you is it depends on what kind of systems you use because see
Which
now
system?
we
What do you
use
mean
something
system?
known as 64. For example, a system as in the the computer system that you use.
Right.
Now we use 64-bit operating systems Before
Yeah.
that, there were 32 bits, there were 16. Of course, in binary, it's better to have multiples of 2.
Hmm.
And the reason you have such blocks of memory, right? Like, for example, if integer is 4,
Hmm.
it starts from an address of maybe 1000 and goes to 1004. Then the 2008, the second country, like you get the idea, right? Array of
Yeah.
memory. So one thing about that is, when you have an integer which fills up like maybe out of 4 blocks, 3 blocks, you can't securely occupy this one because this whole thing will be given to that variable.
Right.
The reason for that is the address lines which go, the silicon address lines which go there, so they are connected to one thing we have called as address gates, which decide what kind of address goes where. So those have certain resolution of maybe 4-bit, 2-bit or something. So that blocks out that whole memory block, and you can't, like if you have a 3-bit variable, you can't put 1 and 1. It doesn't work like that.
You're not allowed to overwrite it and that's interesting because you're saying that it depends, it's a physical consequence, not something that comes as out of logic.
Exactly.
That's actually very interesting. So, like, you're saying that physically the wires cannot take your data types, so we stop it before it tries to.
More than that, like the wires, they are fixed for a certain block. Like these wires will go there. It's not actually wires; we call them buses, address buses.
Right.
So each bus goes to each memory consignment. So you can't take one part like just right. Take one wire here. No, it doesn't.
Yeah.
So one road leads to one place. It just goes there. No matter what you get there.
And for like a different data type, the road would lead somewhere else.
Exactly. Like if you give it some other memory block, it will go only that. No memory. So
Right. Okay.
resolution.
So when you give it a command that takes the wrong data type, then it's essentially trying to force the wrong bus down the wrong road.
Yeah.
Okay.
Kind of.
I kind of get it. Okay, that's what I like, this like physics in these physics comments in the middle.
That's one reason I took electronics.
I wish I could like actually wrap my head around it.
Oh yeah, you can, man.
Oh no, I can't.
Even I don't know a lot, but it takes some time and a little bit of patience. You can do anything you want with that.
True. So much like the data types in computer science and the buses in our circuits, the types on wires tell us what sort of data the process expects as input and what it produces as output. For example, a calculator program expects numbers as inputs and produces numbers as outputs. Thus, can't make sense of Dave as an input, nor will it ever produce, say, carrots as an output. Another useful example is that of electric appliances. Suppose we consider processes to be appliances that have plugs as inputs. So we can have like the UK plug and the European plug. And so using So where we have these plugs as inputs and sockets as outputs. Okay. Then system types are just the shape of the plug, that is UK, European. Clearly, we can't connect a plug to a socket of the wrong shape. So the type of information on the wires gives us precisely the information we need to know which wirings are possible. For example, one possible wiring is what's given over here, matching data types all throughout a diagram. Though this is a toy example, it's very often useful to draw diagrams whose boxes refer to devices that actually exist in the real world. We will refer to such diagrams as operational. So an operational okay, wait. This is not really a rigorous definition at all, so maybe we'll wait for it to come as a topic.
Yeah.
Okay, so you can start process theories.
Yeah, sure. So usually one is not interested in all possible processes, but rather in a certain class of related processes. For example, practitioners of a particular scientific discipline will typically only study a particular class of processes. physical process, chemical processes, biological process, computational process, mathematical process, etc. For that reason, we organize processes into process theories. Intuitively, a process theory tells us how to interpret wires and boxes in a diagram. See 1 and 2 below. And what it means to form diagrams, that is, what it means to wire boxes together. See. So the definition being a process theory consists of a collection T of system types represented by wires, a collection P of processes represented by box, where for each process in P, the input types and output types are taken from P, and a means of wiring processes together. That is an operation that interprets the diagram of process P, processes in P as a process in P. Yeah, it's a little confusing, but yeah, the thing is, right, it's just that process theory is a certain type of wires, a certain type of boxes, and a certain type of kind of a function where you feed these things and it gives us, okay, these are the inputs, these are the outputs, this is what the process is doing. So that's basically what the definition is. You know, people like complicating things.
I think this third one is more of an operation. Yeah, it says here. Yeah, it's an operation that interprets the diagrams. So I think this is very important. It guarantees that process theories are closed under wiring of processes together. Basically, no matter what, in layman terms, if you combine anything from the same process theory, say you have like a huge process theory, you have one process here, you have one process here, then it is a guarantee that whatever composition you do of these two processes is going to lie in this bigger process theory. You're not going to find a way to go out of the process theory. So that I think is important, because if we don't allow closure, then in some sense we're allowing some sort of free structure. I don't know if it's called something. If anything, it may be called something like a free process theory or something. Because generally when things don't have that closure constraint, it's given that free. It's just called free whatever structure it is. So free groups, free monoids, everything's just the same thing, just without closure.
So one thing that might creep up is, as they have given examples of, right, like physical processes, chemical processes, biological processes.
Yeah.
So people might think, when you look at like a certain chemical process, for example, you have two reactants, a process, and there's another part for catalyst. If you look closely under it, if you go like to the surface dynamics of the catalyst, you will go to some part where, you know, it leads more towards physics than whatever chemistry allows you to.
True.
So people might say that isn't closure, but even if you take it in layman terms, if there is any problem of such reading over, just imagine mathematical processes close everything. There is nothing that's not mathematical.
That's very true. Yeah. I like that. Yeah. And another thing is, what do you say? I was telling you about how logic was being used to talk about programming, right? So a part of logic is that, logic is trying to define other mathematical theories, right? And so naturally they try to use logic on logic. And so they kept finding like all these circular arguments that were causing all sorts of issues. And they tried to just outright ban circular arguments from logic, but then it didn't work. So they ended up studying it under co-logic or co-induction. So that's like, I like seeing cameos of whatever I'm studying just pop up here and there.
Yeah. That's very cool.
Yeah, so in conclusion, our process theories are closed under the operation of composing them. And since this is an operation that tells us what wiring together means, in some cases, this operation consists of literally plugging things together like physical wires, like in the example of a power drill. In other cases, it'll need more work, and sometimes there is more than one obvious choice available. We shall see in in 3.2, the traditional math practices typically breaks down the wiring process together as two sub-operations, parallel composition and sequential composition. So this is very similar to parallel and series. So example 3.2, some process theories we will encounter is functions where the types are all sets. So oh wait, okay, right. Okay, so I was thinking of it in a different way. I was confused. So instead of, what do you say? Instead of having sets as the box and functions between them, they have functions as the box and the sets as the data types. Right, okay. Relations are basically the exact same thing, just looser than a function. Linear maps are stronger than a function. Classical processes, types, classical systems, okay. Quantum processes, type quantum and classical systems. Do you have any comments about these two examples?
So yeah, some process theories we will encounter. So when we look at a classical process, like one thing that comes out is, when look at a classical process, usually whatever you do, that whatever you induce in it, whatever you give as input, whatever you get as output, it's always classical. But
Right.
when it comes to something like quantum processes, you need both. You just can't isolate a quantum, like a quantum input and a quantum output. Because one part that pops to my mind is whatever you call
Aren't classical processes just like a subset of quantum processes then?
Exactly. It's very similar to how you look at the whole number systems, domains.
Right.
Like real numbers are still a subset of complex numbers.
Yes.
That also carries us to whatever physics gives you. Whatever you have been, usually, again, there are some gray areas where quantum mechanics and classical mechanics especially don't fit together very well, or somewhere where the quantum definition is exactly opposite of what classical systems is. But yeah, one very beautiful example comes to my mind is, the thing is, I had, it wasn't an epiphany to be exact, but somehow, I had, here as it turns out, people already done it. So when we think of friction, right?
Right.
So there is jagged edges here and jagged edges here.
Yeah.
When we imagine about friction, because everything is microscopically, at least quantumly jagged. Nothing is flat. So first thing that comes to my mind of, when we look at the friction is, there's a statement in when we look at atomic interactions, when two atoms are too close, they'll push each other away, and when two atoms are at a certain distance, they'll pull each other. So at one point of time, they are at a equilibrium. If they come closer, they'll push each other. If they're a little farther, they'll push it. If they're too far, it doesn't matter. So when we look at friction, right, when two surfaces collide, the atoms in the jagged edges, they actually, try to push each other against the flow, right? It's jagged. So it tries to push each other, and that actually creates the friction.
Oh, so it's basically just a set of a whole collection of normal forces, or a whole collection of repulsions.
It's the integral of all that.
Yeah, that's a very cool thought. This is formalized.
Yeah, it's formalized. I don't remember when I read it, but yeah, it is formalized. I'm not sure who, but probably it was Feynman, if I'm not wrong.
Wow. Big name for a big idea.
There's one place where you can see, right, the classical system is still a consequence.
Oh yeah, that's true. Yeah. So friction is purely classical, and you're seeing the only reason for it is basically quantum and just repulsions in general.
Yeah.
Very interesting.
Yeah, indeed.
Okay. So we will use the first two mainly in various examples and exercises, whereas the remaining three will play a major role in this book. Now it's your turn.
Yeah, so remark 3.3. Note how we refer to a particular process theory by saying what the processes are, leaving the types implicit. This tends to be a good practice because processes are the important part. For instance, we'll see that the process theory of functions is quite different from that of relations. So it will not do to just call both sides. Since a process theory tells us how to interpret diagrams as processes, it crucially tells us when two diagrams represent the same process. For example, suppose we define a simple process theory for computer programs, where the types are data types, integer, boolean, list, and the processors are computer programs. Then consider a sort program which takes a list as input and sorts it. It might be defined this way. Don't worry if you can't read the code, neither can me too.
Okay.
So
Yeah.
quick sort. So basically, if I have to explain, like this is basically a list. So in the elements inside the list, this is basically how like quicksort works. This reminds me of I don't know if you have heard like what are they called? Have you heard of what was the name? They use just the angle bracket, the plus and equal to this. It's a Turing complete language. I just forgot its name. Those classes of languages are called esoteric programming languages.
Oh wow! I've never heard of that.
So am I allowed to swear a little because
Yeah.
word is good?
Hello.
Yeah. This language is called brainfuck.
Wow.
So the thing with this language is right.
Yeah.
It just uses angle brackets to angle brackets, plus and minus. It basically, do you know how Turing machine looks?
Yeah.
So it's a strip. You have a reader, and you have something like again, this is the process. This is the input. Whatever you can read out of it is the output, right? And then Turing machine is actually a process.
True.
Yeah, you use the angle brackets to shift it, and you use plus and minus to increase or decrease the number of whatever bits are there. So you can use that to write a whole program, and it's very weird that the program is Turing complete. So yeah, it's called brainfuck, and there are many other esoteric programming languages. I've forgotten the name, but the whole class of them basically revolves around something like breaking down the process to the least possible, like understandable chunk.
But how did Quicksort remind you of this?
Sorry? The pluses and the angle brackets and all those, right?
Right.
Yeah. So, being a Turing complete language means it can also implement Quicksort. So I just, my mind just
really?
instead of thinking, okay, how can you make Quicksort in brainfuck?
Maybe we should do a video on that.
We're trying, but I'm not going to do it. I'm really bad at programming.
Me too. Both of us. And I have to code for the rest of my life now. Right, go on. So
yeah, okay. Why it's just, I guess, yeah, I'm not really good at reading the code, but
yeah, I'm not
this
sure what this angle means.
This is the pointer which goes into the list.
Which assigns this to that.
Yeah. This increments after every cycle. Here, it checks whether y is greater than x. If it is, it swaps. Else, it just moves forward. So this is basically, I guess, what works.
Right.
Wiring together programs means sending the output of one program to the input of another program, taking two programs to be equal if they behave the same, disregarding some details like execution time. Our process theory yields equations like this method, quicksort and quicksort. Like this is what basically kind of what closure was, like this part of closure was looking at.
Yeah.
So
we've composed them. and we get just something that was already there.
Yeah, exactly. So one other interesting point I would like to make here is in C programming we have like type declarations for the functions, right? Like a function can return a void or you declare it at the start with the function's name like main or void name. So basically, if we take those functions and processes, right? So if you have the chain of those two processes, the type should match. It's like just giving an idea of how processes and
right. So like when you're passing your variable, it should be the same data type that you're passing it to. Yeah, right. And another thing I just want to note, if we, like, I'm sort of thinking algebraically, so in some sense, this looks like, composing this, like, let's just take this process to be X. And so we have X compose X is equal to X. And so if I want to write it questionably, if I want to write it as X squared equal X, then I don't know, this somewhat reminds me of split complex numbers. Maybe not, but there might be some way. There might be some way to like map actual like algebras to these process diagrams.
I mean, split complex numbers it's actually very interesting thought, like every complex number can be split into two complex numbers, basically.
No. That's not what we mean by split complex numbers. So split complex numbers, we'll talk about it later on a different video because that's like a huge thing. So it's like basically we have I squared equal -1 for complex numbers, right? So similarly, we have to adjoin a new unit I to make complex numbers. Similarly, if we choose to adjoin a new unit but with a different relation, so now we're going to introduce j squared equal +1. And we're going to say j does not actually belong to the real numbers a priori. And we're adjoining this as a unit. And so suddenly you have a new system called the split complex numbers. And the split complex numbers, like basically all I see them in is special relativity. Because like anytime I Google it, I hear something Lorentz. Like anytime I want to look for it purely for the sake of split complex numbers, Lorentz just pops up. So what it has to do is so you can have like Euclidean 3 space and it's sort of dual, like its counterpart thing is like Lorentzian 3 space. So when the way I came across these is that they were studying minimal surfaces that exist in Euclidean 3 space, and they found it useful to study maximal surfaces in Lorentzian 3 space. And so what ended up happening is that the Lorentzian 3 space is like, very close to how split complex numbers are defined. And so as a consequence, studying maximal surfaces in this ended up forcing them to study split complex numbers more deeply. So things like changing parameterization of your surface from your Euclidean 3 space to your Lorentzian 3 space. That would involve something of mapping your normal real function to its split complex counterpart. So that's the context I came across it in.
That's very cool. It's new for me.
You will probably see it around a lot more now that you know it exists, because it's unexpectedly common. You will notice yourself like taking roots of something equal to 1, and like now you're gonna like blink twice. You're gonna be like, wait a minute.
Nice. Yeah.
So the reason we call a process theory a theory is that it comes with lots of such equations, and these equations are precisely what allow us to draw conclusions about the processes we are studying. So that's interesting. So basically, so a process theory has equations like this, and when you have like, say on further on this side you have more equals to something else and so on and so on. So that set is of whatever you're equating it all to is going to form a equivalence class, right? So in some sense, a theory is a set of all these equivalence class that you can make out of these processes. So in some sense, you say a theory is like just the union of all these equivalence classes, and these equivalence classes are going to like, partition this entire theory into these smaller subsets of where everything is the same equation. And it comes with all these equations. To take another example, the function we defined at the beginning lives in the process theory of functions. The types are sets and processes are functions between sets. We consider two functions equal if they behave the same, that is, they have the same graph plot. Note how two input wires means a function of two variables, hence a 3D plot, since they have the same graph. Since they have the same graph, we have this equivalence relation. Not equivalence relation, this equation. So, on the left side we have our original equation, just as is. But on the left side, what we do is we take our input first. First we square it and then we add it, instead of taking it directly. So in some sense, this is like decomposing the whole thing. Another interesting one is that just negating a function twice is the same as doing nothing. So, like, you have minus 6.
Minus 1.
Yeah, minus 1 into minus 1 is 1. Yeah.
I mean, with that, that's right. My math professor had given a very good analogy. So now you're facing east. Right?
Yeah, right.
Just imagine
rotate west once.
Rotation. Just turn 180, turn 180 again.
You're facing the same way. Yeah.
It came up because we had some speech thingy, right, in my class. So some guy, while trying to speak about how he changed something in his life, he told that he did a complete 360 in his life. So that means he was back to his bullshit. So,
you haven't changed.
Professor pointed it out, and
it's supposed to be a 180.
Yeah, I mean, back to 360 means I'm back to my own. So do whatever you want. I'll save myself.
Poor guy catching strays in the middle of a motive. Huh?
Yeah, until where are we covering right now?
I think
would be feasible to stop.
Yeah, because it ends with an exercise, so it's almost like telling us, like, okay, you can stop here. Yeah, cool.
Please let me breathe a little.
So, page 40.
Yeah, we can take up diagrams and mathematics.
I think, we've actually done 1 hour of talking.
Ooh.
Yeah. Longer than 1 hour, including all the sending the PDF.
Yeah, very good.
Okay, cool. So, we will stop there.
Yeah.
Thank you for watching. Catch us at the next lecture.